Hello everyone. This week's lecture will cover Part 2 of Module 13. Here in Part 2, we will discuss ethers. Ethers are a class of organic compounds that contain an ether group, which consists of two alkyl or aryl groups bonded to the same oxygen atom. The general formula for an ether is ROR prime, where R and R prime represent the alkyl or aryl groups. An example of an ether is diethyl ether, which has two ethyl groups bonded to the same oxygen atom. Ethers have important uses in our everyday life. You've probably encountered or used an ether but were not aware of it. For instance, dimethyl ether or DME is used as an aerosol spray propellant and refrigerant. Diethyl ether is used as a starting fluid for diesel and gasoline engines. It used to be also used as an anesthetic. Ether compounds can also be found in nature. For instance, anisole or methoxybenzene is an aryl ether and a major constituent of the essential oil of anise seeds. Many vapors that contain ethers are used as insecticides, miticides, and fumigants for soil. Here are some physical and chemical properties of ethers. Compared with alkanes of similar molar mass, an ether will have a similar boiling point. Compared to an alcohol of the same molar mass, the ether will have a much lower boiling point. Here are examples of an alkane, ether, and alcohol. The alkane and the ether have the same boiling point of 36 degrees Celsius and 35 degrees Celsius respectively, whereas alcohol has a boiling point of 117 degrees Celsius, despite them having almost the similar molar mass. Furthermore, ethers are more water-soluble than alkanes because water molecules can form hydrogen bonds with them. An ether and an alcohol of the same molar mass has about the same solubility in water. Ethers are highly flammable. The boiling point of diethyl ether is 35 degrees Celsius and ether vapor ignites readily. Ethers react with oxygen to form hydroperoxides and peroxides, which are unstable compounds that can explode. Ethers react similarly to alkanes in combustion and halogenation reactions. Ethers are named somewhat differently from the other hydrocarbons we have discussed so far. For instance, the parent chain name does not have a unique suffix like "ol" for alcohols. In ethers, the parent chain name is whatever the name of the LCC is. So for instance, if the LCC is pentane, then the parent chain name is pentane. The identifying name of ethers is in its substituent. Substituents are named as an alkoxy substituent, where the "-il" part of the alkyl chain name is changed to oxy. For example, when methyl is the alkoxy substituent, its name becomes methoxy. Alkoxy substituents are also numbered. The number starts from where the oxygen atom is attached to the LCC or the substituent. The final name of an ether is arrived at by simply adding together the alkoxy name and the parent chain name. Let's try naming these ethers. For ethers, we must first choose which side of the oxygen has the LCC. In our first ether on the upper left, the left side of oxygen has 4 carbon atoms with single bonds, so it is an alkane. The right side is also an alkane but only has 2 carbon atoms. So, the carbon chain on the left is the LCC. Since it has 4 carbon atoms, the parent name is butane. The shorter carbon chain becomes the alkoxy substituent. In this case, we take its name and change the "il" to oxy. So we have ethoxy. Then we indicate the carbon number on the LCC to which the oxygen atom is attached. In this case, it is attached to carbon 1. We put together the name of the substituent and the parent chain name to arrive at the full name of the ether, which is 1-ethoxybutane. Now we go to the ether on the right side. This ether has a 5 carbon atom chain on the right side and a 1 carbon atom chain on the left side. So, the chain on the right side is the LCC. A 5 carbon alkane is called pentane. The alkoxy substituent is methoxy. The oxygen is attached to carbon 2 of pentane. So, the full name of this ether is 2-methoxypentane. Now we go to the last ether. This ether has a 3 carbon chain on the right side and a 1 carbon chain on the left side. So the LCC is the 3 carbon chain propane. This propane has a methyl substituent attached to its carbon 2. So we include that in the name for the LCC. We have propane and 2-methyl. Then we attach the alkoxy substituent on the left side of oxygen, which is 1-methoxy. Thus, the full name of this ether is 1-methoxy-2-methylpropane. Note that when naming this ether, we name the right side separately from the left side, including whatever substituent is attached to them. Now let's try naming these two compounds. The first compound has 2 alkane chains attached to the oxygen atom. First, let's determine which chain is the LCC. On the left side of the oxygen atom, we have 1, 2 carbon atoms. A 2-carbon alkane substituent is called ethyl. The other side of oxygen has 1, 2, 3, 4, 5 carbon atoms in the parent chain and 1 substituent with 1 carbon atom. A 5-carbon alkane chain is called pentane. So, since it has more carbons than the alkane chain on the left, pentane is our LCC. The methyl attached to pentane is attached at carbon number 4. So we write here 4-methyl pentane to complete the parent chain name. Then we add the left side of the oxygen atom by first replacing the suffix "il" with oxy to get ethoxy. So we write here ethoxy. Then we add the carbon number to which the oxygen is attached, which is 2. So the full name of this compound is 2-ethoxy-4-methylpentane. The next compound has 2 functional groups. Here we have an ether, and over here we have an alcohol. In this case, naming the parent chain is based on priority. Alcohols have a higher priority than ethers in parent chain names, so alcohol names will automatically be the parent chain between these two functional groups. On the right side of oxygen, we have a 1-carbon chain. On the left side, we have a 1, 2, 3, 4 carbon alcohol. Numbering is from left to right because the hydroxyl group has higher priority than the ether group. A 4-carbon atom alcohol is called butanol. The ol or the hydroxyl group in butanol is attached to the second carbon. So we write 2-butanol. Now the right side of oxygen is a 1-carbon atom called methyl. To change the name to ether, we simply replace il with oxy. So this is methoxy. Methoxy is attached to the butanol at carbon 4. So we add 4 here to complete the name of this compound, which is 4-methoxy-2-butanol. Isomerism, or the state of compounds having the same molecular formula but different structures, can occur in ethers. Because ethers contain carbon, hydrogen, and oxygen atoms, the possibilities for isomers is greater than for hydrocarbons. For example, an ether having 3 carbon chains will have the following constitutional isomers: 1-ethoxypropane, 2-ethoxypropane, or 2-methoxybutane. Ethers have an alternative naming system that is often used for those with simple alkyl groups. This naming system combines the name of the alkyl on the left and right of the oxygen atom, then adding the word ether to arrive at the full name. When both alkyl groups are the same, the prefix di precedes the name of the alkyl group. For example, this ether has an ethyl on both sides of the oxygen atom. We combine the alkyl name on the left with the name on the right, and since both alkyls are the same, we add the prefix di before the alkyl name. Thus, the common name of this ether is diethyl ether. The IUPAC name is ethoxyethane. Here are other examples of the common naming system for ethers with simple alkyl groups. In our first ether, we have an ether with an ethyl and a methyl group on either side of oxygen. Its IUPAC name would be methoxyethane, but we can also name it as ethyl-methyl ether. Note that the alkyls are arranged alphabetically rather than by length of carbon chain. In our second ether, we have an ethyl on the left side and a propyl on the right side with a halogen as a substituent. The halogen is chloro. The IUPAC name for this ether is 1-chloro-3-ethoxypropane. The common name is 3-chloropropyl ethyl ether. Remember that when naming ethers, we name the right side separately from the left side, including the substituents that may be attached to it. Let's practice naming these two ethers using the common naming system. The IUPAC name of the first ether is 1-ethoxy-4-methylpentane. To get the common name, we simply name the chain on the left side and the right side of oxygen separately first, then put them together alphabetically, then attach the word ether. The chain on the left side has 1, 2 carbon atoms, so its name is ethyl. The chain on the right side has 1, 2, 3, 4, 5 carbon atoms, so its name is pentyl. Pentyl has a methyl substituent in carbon 4, so we attach methyl to the pentyl name and add the carbon number. This gives us 4-methylpentyl. Then, to get the full name, we arrange ethyl and methyl alphabetically. Since E comes first before M, we write ethyl, 4-methyl, pentyl, and then attach the word ether. So, the full name of this compound is ethyl 4-methylpentyl ether. Now let's go to this other ether whose IUPAC name is 2-methyl-2-propoxypropane. Let's name the chain on the left side of oxygen first. This chain has 1, 2, 3 carbon atoms and 1 substituent which has 1 carbon. A 1 carbon substituent is called methyl. So its name would be methyl propyl. However, this arrangement of carbon atoms is also the structure for the 4-carbon atom tert-butyl. Now, the carbon chain on the right side of oxygen has 1, 2, 3 carbon atoms, so its name would be propyl. So we have propyl and tert-butyl on either side of the oxygen atom. To get the full name of this compound, we simply arrange the names alphabetically. Note that the word tert is not included in the alphabetical arrangement because it refers to the name of the structure and not the name of the alkyl itself. So the correct name of this compound would be tert-butyl propyl ether. Ethers can form cyclic compounds which are called epoxides. Cyclic ethers are similar to cycloalkanes or cycloalkenes, but they possess an oxygen atom as part of the ring. Cyclic organic compounds in which one or more carbon atoms of the ring have been replaced by atoms of other elements are called heterocyclic organic compounds. Examples of epoxides are ethylene oxide, tetrahydrofuran, furan, and pyran. Although cyclic ethers have IUPAC names, their common names are more widely used. In the common naming system, the prefix ox is used to indicate the presence of an oxygen in the ring. The suffixes irane, ethane, olane, and ane show 3, 4, 5, and 6 atoms in a saturated ring respectively. So, oxyrane has 3 atoms in its ring. Oxetane has 4 atoms, oxolane has 5 atoms, and oxane has 6 atoms. A cyclic ether with 6 atoms in its ring, wherein 2 of those atoms is oxygen, is called dioxane. An ether can react with a concentrated acid such as those formed by iodine or bromine to form an alkyl halide and an alcohol. The reaction proceeds as follows. Here is an example of a reaction of an ether. We have dimethyl ether reacting with hydrogen bromide. In the presence of heat, this reaction produces methyl bromide and methyl alcohol. When methyl isopropyl ether reacts with hydrogen iodide, it produces methyl iodide and isopropyl alcohol. That's it for our lecture on ethers. In this lecture, we learned that ethers are derivatives of hydrocarbons with an R-O-R' functional group. Ethers are named as alkoxy substituent plus parent chain name. Ethers can form cyclic compounds called epoxides, which are known by their common names. And ethers react with concentrated acids to form an alcohol and an alkyl halide. And that ends part 2 of Module 13. Module 13 and 14 will have a combined activity worksheet. Please refer to Module 14 for the activity instructions. Thank you for listening.